Okay, so as promised, I'm going to do a second stoichiometry example using the method of the turnover table that I just explained in the first stoichiometry video. Obviously, you should watch that one before this one. And I just want to reiterate the general logic that we're using to proceed with these stoichiometry questions, right? We're going to build a turnover table that tells us how the reaction works in number world, where we're counting numbers of each reactant molecule and figuring out how much, in terms of numbers, we can make of each product molecule. And so in order to use that, we need to jump in by converting mass to moles. We need to figure out the moles of whatever starting compound we're given. And then we can use that in the context of our turnover table to convert the moles of our starting compound into the moles of the desired compound. Okay? And then we're going to jump back out using moles to mass, right? So whatever we figured out the moles of our desired compound, all that's left is to convert that back into a mass, which will answer typically whichever question we've been asked. So the example we're going to do now involves CO2 scrubbing, so chemical scrubbing of CO2. If you're living in an underwater vessel like a submarine, which is fully enclosed, or if you're in outer space in a confined volume, you need to obviously breathe, so you need to have oxygen in the air, but you also need to be able to get rid of the respiration waste product of CO2, because if that builds up to toxic levels, you're going to be in trouble. And so chemical scrubbing is a way that can be done, and lithium hydroxide is a compound that can be used to chemically scrub carbon dioxide out of the air. And so this question is asking us how much CO2 we could scrub out of the air if we're using up 1 kilogram, 1.00 kilograms of lithium hydroxide. So the first thing we need to do is write down the chemical equation and see if it's balanced. So pause the video and take a second and balance that equation. It's good practice. Okay, so if you've come back, you should notice that, well, for one thing, the very first atom, lithium, isn't balanced. In order to get 2 lithiums on the right-hand side, I'm going to need to put a 2 coefficient out here. Okay, and now I go through and I check my next atom. Okay, well, let's check hydrogen, because hydrogen is only in one compound on the other side. Looks like I have 2 hydrogens on that side, I have 2 hydrogens on this side, so hydrogen's looking pretty good. Carbon is 1 carbon here, 1 carbon here. Carbon's looking good. So the only thing left is the oxygens, and we're looking pretty good there, right? We've got 2, and 2 is 4, 3, and 1 is 4. So that equation is balanced. Okay, so once we've got the balanced chemical equation, it's worth it to rewrite it. So we have a little bit more space here. For our turnover table, okay, and so we're going to need moles and turnover. All right, so obviously what we need to do is we need to be able to jump in. We know that we're going to be able to use that balanced chemical equation to figure out how the moles of one thing relate to the moles of something else, but we need to have a moles to start with. And so that's our jump in. And so we're going to jump in by converting 1.00 kilograms, which I happen to know is 1.00 times 10 to the third grams. You can do that with a separate unit conversion step, but in honors chemistry, you can also just write it down if you know how to do that. Okay, and then we are going to convert that into moles by multiplying by 1 mole divided by 23.95 grams, and that is, of course, the molar mass of lithium hydroxide. And so this tells us that we're going to get 41.8 moles of lithium hydroxide to work with in our 1 kilogram. So let's put that in the turnover table. Now we need to stop and take stock. Remember what the fundamental question and the point of using a turnover table is. We need to figure out how many times we can do this chemical reaction starting with the moles of the stuff that we put in our turnover table. So we jumped in with our 41.8 moles of lithium hydroxide. How many times are we going to be able to do the chemical reaction? Pause the video and see if you can figure this out on your own. Think carefully. Okay, so I found that this time is something where students almost always make their first mistake in this stuff, even if everything's made sense up so far. Okay, we have 2 lithium hydroxides required for every carbon dioxide. So what this means, if you were to flip this on its head, it would say, if I wanted to get rid of 1 molecule of carbon dioxide, I'd need 2 formula units of lithium hydroxide. If I only had 1 formula unit of lithium hydroxide, I wouldn't be able to do anything until I got more. Okay? So that means I need 2 of these for every 1 of those. So that means the number of times that I can turn over the reaction is only going to be half of the number of moles I had, right? In order to turn it over once, I need 2 of these. In order to turn it over 1 mole of times, I need 2 moles of lithium hydroxide. So if I'm starting with 41.8 moles of lithium hydroxide, that means I'm only going to be able to turn the reaction over half as many times, 20.9 moles. And this should make you feel good because it does preserve that relationship I pointed out in the last video, that the turnover number times the stoichiometric coefficient always needs to be equal to the moles. So if you've got a number that's bigger down here than the number in the moles line, you've probably made a mistake. Either that or you're using a non-standard chemical equation that has a 1/2 up here. It's not impossible for that to happen, but that's generally more advanced, and we're not going to see that for a few units. So right now, it would be a probably pretty sure sign that you made a mistake if your turnover number is ever bigger than the number in your moles line. Okay, so now we figured out how many times we can do the reaction. We can carry that number over to the compound we're interested in and figure out how many moles of CO2 we're going to be able to use up. And since the stoichiometric coefficient on CO2 is just 1, that's going to be the same. This tells us it's going to be 20.9 moles of CO2 that are absorbed by our 1.0 kilogram of lithium hydroxide. So in some sense, that answers the question. All they said was how much CO2 gas. So certainly this is a number. I'm saying it's 20.9 times 6.022 times 10 to the 23rd molecules of CO2. So that is certainly saying how much. But of course, in a normal problem, we'd want to know the mass. And in order to get that, we need to jump out and convert that mole number for CO2 into a mass. Pause the video, do this on your own. Make sure you can do this. Should be almost as easy as breathing at this point. We're going to multiply by the molar mass of CO2, which is just 44.01 grams per mole. And so that's going to leave us with 920 grams of CO2. And of course, because I had 3 sig figs up here, I represent 920 in a way that unambiguously has 3 significant digits, which takes us back to Unit 1 where we covered that stuff. Okay? So, this is another example, and I urge you to go ahead and complete this turnover table. Fill it out. Figure out what mass of lithium carbonate would be produced by this reaction, right? We're basically turning the lithium hydroxide into lithium carbonate by absorbing all that CO2, and in the process, we're producing some liquid water as well. So go ahead and figure out what mass of liquid water we're making. That's for you to do on your own. At this point, you should be able to do that, but certainly feel free to send me a message through the portal if you have any questions about this. There will be a discussion question on the portal for you to do. It will be due on Thursday night. Okay, so make sure you go through this stuff, watch this video once, twice, and answer that discussion question. All right.